Let us start chapter 3, section 3. Problem number 1, let's maximize our objective function z is equal to 40x plus 12y, subject to our constraints. So here let us make a table for the first inequality, and let's make another table for the second inequality. And let's use the intercept method here. So when x is 0, we have negative 2y is less than or equal to 12. Dividing both sides by negative 2, we have y is equal to negative 6. And when y is 0, we have 12 divided by 6, which is equal to 2. Second equation, inequality I should say, let's let x equal 0. So here we have y is less than or equal to 9. And when y is 0, we have 9 divided by 3, which is equal to 3. So we have 3, 0. So let's draw these two inequalities. We have 0, negative 6. So again, if this is 0, negative 6 is somewhere down here, which we don't care about that point right now. But we do want x is equal to 2. So we have 1, 2. So here we have 1 point, and let's draw the line. So say negative 6 somewhere down there. And here we have less than or equal to. So less than or equal to is to the left. Now let's draw the second inequality. We have 0, 9. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And 3, 0 is here. So 0, 9, 3, 0. And let's connect those points. And we have this line. And again, less than or equal to is to the left. So less than or equal to is here. So here we have our point of intersection and our feasible region. So less than our feasible region is enclosed by these 4 corner points. 1, 2, 3, 4 corners. So let us write our corners. 0, 0 is our first corner. 0, 9 is our second corner. Here our point of intersection is 2.5, and it's actually 1.5. And here we can solve this point by elimination, which is the addition method. So you can solve that point of intersection by either the elimination or the substitution method. And the last point, corner point, is 2, 0. So now once we have our corners, let's substitute each point into our objective function. So 40 times 0 plus 12 times 0 is equal to 0. 40 times 0 plus 12 times 9 is equal to 108. And z is equal to 40 times 2.5 plus 12 times 1.5, and that is equal to 118. And 40 times 2 plus 12 times 0 is equal to 80. Looking at our results, 118 is our highest number. Therefore, our maximum number is 118 at the point 2.5 and 1.5. Number 2, here we have a minimizing problem. So let us minimize this objective function. So before we do that, looking at our first inequality, let's get rid of this fraction by multiplying all terms by 2, which will make it easier to solve. So let's multiply all terms by 2. So here the 2's cancel, so we're just left with 1x. 1x minus 2y is greater than or equal to 4. Okay, now we can make a table like we did before. And we can make a table for the second inequality as well. So for the first inequality, when x is 0, we have negative 2y is greater than or equal to 4, dividing both sides by negative 2. We have 4 divided by negative 2, which is negative 2. And then when y is 0, we have x is equal to 4. In our second inequality, we do the same thing. When x is 0, we have y is 7. When y is 0, we have x is 7. And now let us draw our graph. 3, 4, 5, 6, 7. So again, we have 0, negative 2, which is not part of that graph. 4, 5, 6, 7. Because we just want x and y is greater than 0. So 0, negative 2 is somewhere down here. And 4, 0 is there. So drawing that line looks something like that. And greater than or equal to is to the right. Now the second table, we have 0, 7, 7, 0. And our graph looks something like that. And greater than or equal to, again, greater than or equal to is to the right. And look at our feasible region is right here. So our corner points are 1 and 2. We only have 2 corner points here. And they're bounded by 7, 0. And this point can be solved again by either elimination or substitution. It looks like it is 6, 1. And let us substitute these points into our objective function. So z is equal to 130 times 7 plus 120 times 0. And that is equal to 910. And z is equal to 130 times 6. Plus 120 times 1, and that is equal to 900. And 900 is our minimum value. Therefore, the minimum number is 900 at 0.61. Now let's look at number 3. Here we have a word problem. So let's read this word problem carefully, and let's determine what our objective function and our constraints are. So here you have a dietitian that has 2 foods. Container A has 1 unit of additive 1 and 1 unit of additive 2. Container B contains 1 unit of additive 1 and 2 units of additive 2. The patient needs at least 5 units of additive 1. So again, we know at least is our inequality. And at least 6 units of additive 2. How many containers of each food should the dietitian use to meet the patient's needs? And find the minimum cost if food A costs $3 and food B costs $3. So here, if we let x is equal to food A, and we let y is equal to food B. So here we know at least, the patient needs at least 5 units of additive 1. So at least is greater than or equal to 5, and this is going to be our additive 1 inequality, and at least 6 is greater than or equal to 6, and this is going to be our additive 2 inequality. So looking at our sentence, food A contains 1 unit of additive A, so we have 1x, and additive B again is the same, is 1 of additive A. And then for additive 2, we have food A contains 1 of additive 2, so we have 1x. And then B contains 2 units of additive 2, so we have plus 2y. So here we have our 2 inequalities. And again, we continue with making a table and plotting our points. So when x is equal to 0, we have y is equal to 5. And when y is equal to 0, x is equal to 5. And then we do the same thing for the second inequality. When x is equal to 0, you have y is equal to 3. And when y is equal to 0, x is equal to 6. So we have 0, 5, 1, 2, 3, 4, 5. So we have 5, 1, 2, 3, 4, 5. And here is our first line. And greater than or equal to is shaded above. And our second inequality, we have 0, 3, 6, 0. And here let us draw that line, and again greater than is above, so our feasible region is right here, and it is bounded by 3 corner points, 1, 2, 3. And here, because we want to minimize our function, so we want to minimize our cost, and our cost is $3 for food A plus $5 for food B. And again, this is our objective function. So let us write this objective function down here. And let's substitute our corners into our objective function. So our corners here, we know this corner is 0, 5. This point of intersection is solved by either elimination or substitution, or by looking at the graph. And we can see that it intersects at approximately 4, 1. And the last corner is 6, 0. So substituting those points into my objective function, we have 3 times 0 plus 5 times 5, and it's 25. Here, 3 times 4 plus 5 times 1 is 17. 3 times 6 plus 5 times 0 is 18. And here is our minimum number. Therefore, the minimum cost is $17 at 4 containers of food A and 1 container of food B. And this concludes part of Chapter 3, Section 3.